Okay, um, welcome to the next video on background on bonding and consequences on structure. So what we've been building up to is an understanding for all the intermolecular forces and intermolecular forces that might be responsible for properties in matter. Okay, so at the end of the day, we need to understand things like cohesive forces and how they might predict things like certain physical properties. So we spoke a little bit about the scenario for how covalent bonds are formed, and you can see here that covalent network solids like diamond with fourfold bonding through sigma bonds from carbon throughout lead to the structure of diamond. Very strong bonding circumstance there. Ionic solids are competitive with that. So things like the force of attraction between oppositely charged ions in NaCl as an example is very strong bonding in 3 dimensions. And going down the case when 3-dimensional network bonding doesn't exist in covalent networks or ionic solids, and we go to more localized bonding circumstance like free molecules, we need to understand intermolecular forces and how things like the water molecule bind to other neighboring water molecules and apply that to other similar materials that have different molecular structure. Okay, so with that, we're now ready to better understand bonding and other materials like ionic bonding. And again, the importance is being able to relate the bonding circumstance in all 3 dimensions to the physical properties. So we might expect that by increasing the cohesive forces between atoms in a structure or molecules in a structure that we would impact things like boiling point and melting point. So if there are stronger cohesive forces holding units, atoms, molecules, etc. together, it's going to take more energy, more temperature to boil or to melt the material to allow certain bonds to break and to dissociate the molecules from each other, or to dissociate bonds and release atoms from each other. Okay, so we've seen our planetary model for ions before, so we'll use that again here to just understand the formation of ions in the example of sodium chloride. So here we have the beginning scenario of sodium neutral and chlorine neutral. We would predict that sodium is the 11th element in the periodic table, so there should be an electron configuration of 1s2, 2s2, 2p6, that's 10, and then a 3s1. So this is reflected in the planetary model down below, where the outermost orbital, the largest, the 3s orbital, has a singly occupied electron. If we lose that electron, the remaining electron configuration for sodium becomes equivalent to that of the noble gas neon, which is 1s2, 2s2, 2p6. So losing that last electron actually allows for the ion of sodium, sodium plus, to have the same electron configuration as a noble gas and to be very stable. So there's a driving force to do so, therefore. Chlorine neutral has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. It is 1 electron away from having its 3p orbitals filled to give us the electron configuration of argon, which would be 1s2, 2s2, 2p6, 3s2, 3p6. So if we could gain an electron in that p orbital, we would complete that outermost shell, and the electron configuration would look like the next nearest noble gas of argon. And again, that is a driving force to acquire an electron from chlorine neutral to chlorine ion chloride. So after the electron transfer has occurred, we see a missing electron in the transformation of neutral to sodium ion as its cation, and then we see a gain of an electron into that outermost shell in the formation of chloride. We'll touch on this a little later, but in doing so, there's now more positive charge per electron count. So actually, the cation here is expected to be even smaller than the diagram predicts. So cations generally are smaller. So cations contract as we form them in comparison to their neutral state. And then anions, because we've added electrons and there's now electron-electron repulsion, anions typically are larger, and anions add volume to accommodate that extra electron. Okay, takeaway here is that we now have opposite charges, negative and positive, and opposites attract, and so we'd expect some attractive force between these two as we consider the ionic bonds. Okay, let me just clear this up. So what we're going to look at in more detail now is the type of bonding associated with ionic bonds, and in later videos, covalent and metallic bonding. Okay. As you've seen before, materials like ceramics and glass are generated by forming ionic bonds, and these generally combine a metal and a non-metal from the periodic table. Whereas for this course, we're going to consider polymers and semiconductors made generally through covalent bonding. Okay, generally non-metals with non-metals, or semi-metals with themselves, or semi-metals with non-metals. And then, of course, the metals we're used to are going to involve metallic bonding, as we'll see later. Okay, so hopefully you followed the analysis there where we showed how sodium started with 11 electrons in its neutral form. We saw that the outermost electron was located in its third level, that 3p orbital, 3s orbital as its final electron. And of course, we recall that the nucleus, if neutral, should have the same number of protons as the number of electrons, again when neutral. And so we have electrical neutrality by balancing those two together. Over in the neutral chlorine, we were one electron away from a argon electron configuration, so that is the 3p5. Explain the 3p has the last 5 of the 17 electrons in that atom, and again we're in the third level there. And again we have electrical neutrality in that neutral case. Okay, and then following that transfer, we have formed ions, the sodium cation and the chloride anion, and we see that an ionic bond can now form because we have charges. So showing that here by just taking an examination of everything again. Now notice that we have 10 electrons in the sodium cation, and now a gain of 1 electron when we consider chlorine forming chloride. Number of protons has not changed, and our electrical neutrality has been removed because we have an additional electron, so we're overall -1 in charge. And we have more protons than neutrons over in the cation, so we're overall +1 in charge in sodium cation. Okay, so we're now prepared to understand the Coulombic attraction that occurs between these two ions. And so the Coulombic attraction is the force of attraction between oppositely charged species, and it's directly proportional to the inverse of the distance between charges. So putting an equation to that, we would expect the force of attraction to vary as the inverse of the distance between the two. So let's call the distance between the two A as an example. Not only does it go inverse with that, but it goes inverse to the square. So small adjustments in the distance between the two ions, nucleus to nucleus A, lead to big changes in the force of attraction between the two. Okay, so this graph is similar to a 1 over x squared graph, and so we expect a lot of characteristics like this. Okay, so we'll build off that in the next slide here. Here's the two ions in question, sodium cation and chloride anion. And you can see here that we've put the label for the distance between the two as A, so notice it's nucleus to nucleus. And so we could imagine a scenario where they're very far apart and there would be very little force of attraction between the two. So in this case, we've labeled that as FC, the Coulombic Attraction, FC. All the data here is positive, so there's positive force of attraction in all scenarios. And as we make small adjustments in the space between the two ions, we make relatively large adjustments in the force of attraction between the two, or the Coulombic attraction force between the two. Elaborating further on this, rather than just having a proportionality between the two, we can now actually fully describe it with some additional details that we know about the atom. So we know that the numerator can take the form of a constant here, so the Coulombic force of attraction will be equal to the negative of a overall numerator, given k temporarily here. The negative sign accounts for the fact that we have opposite charges, so we'll have a minus and a plus that are going to be in this numerator, and so we need to get rid of the product of the negative sign there with an additional negative sign out front of the k to give us the positive data that we have in our graph. And we've still got the denominator here of the internuclear distance A, of course, to the square. Okay, so what's going on in that numerator, K? Well, we see here that K has some information about the charges. So we see here that Z is the valence of the charged ions. So Z1, 1 representing the first atom. So for us, this could be the Z of the sodium plus cation. Z here is going to be +1 in value. So the input into the equation would be a +1 at that point. This also follows that the Z for the anion, Cl minus, would be -1, and that would be the second Z value here. Okay, because we've only accounted for charge at this point just using integers, we want to actually bring in some charge units, so coulombs of charge, and so we're going to use the charge of the electron for this. So we'll use Q again. So in your textbook, this is listed as 0.16 times 10 to the minus 18. We've previously used this as the equivalent of 1.6 times 10 to the minus 19 coulombs for the charge of an electron. Okay, so you can see here that that shows up twice in both parenthetical components of that numerator. We have Q and Q in both terms, and we have the integer multiple of the charge reflected in the Z value. In an example where we say had magnesium 2+, we'd expect a Z value for Z1 as an example to be +2 as the input at that first Z position for the cation. Okay. And the final value here is the K0. So here we have a proportionality constant, and so it's going to be 9 times 10 to the 9 voltmeters per coulomb. Voltmeters per coulomb. Okay, and so we'll handle the units there in a moment. So all of that divided through by the square of the distance between the two is going to give us an attractive Coulombic force in units of newtons. Notice again that we should be using values here in SI units. So the distance between the two should be input, that is used in the equation, in meters when we use this equation. And for sake of easy depiction of distance on this graph, we've here plotted in nanometers. So be careful with what input you use in the Coulombic force of attraction equation. Use SI units of meters. Okay, let's just clean some of this up. Very good. Okay. So we saw in the previous graph that if we bring the two ions of opposite charge closer and closer together, we get increasing force of attraction between the two, or a Coulombic force. And of course, this would just go upwards to infinity, provided we can bring the nuclei closer and closer together. Now, of course, at some point, there would be the nuclei that are positive in here, and a repulsive force would occur. So the force of repulsion is because at some point, the protons in the nucleus are going to repel the protons of the neighboring nucleus, and we're going to have an opposite force, a force of repulsion. And that largely follows an exponential as well, this time in the opposite fashion. So the repulsive force is going to give us a negative contribution if we bring the two too close, the two nuclei too close to establish the ionic bond. And so you might imagine that at some point, the Coulombic force of bringing these two oppositely charged ions towards each other will equal the repulsive force that wants to push them away due to the nuclear-nuclear repulsion. So this leads to the idea of an equilibrium bond length, where at some ideal distance between ions, we've balanced the force of attraction with the force of repulsion, and we establish the bond length. Okay, so this force of repulsion actually follows an exponential, as we mentioned here, and so the force of repulsion goes as e to the negative a over r. And here you can see that there's some experimentally determined constants for the ion pair. So every ion pair has different lambda and rho values here, and they need to be calculated. So we won't be handling this equation with a lot of detail, but there is some data out there for every ion. Okay, so if we're following this sum graph, if we're kind of mathematically adding these two dotted curves together, we end up with the result here in the solid line. And I'll just get rid of my earlier one so it's a little more clear. There we go. So that solid line represents now the mathematical sum of both curves, if you want, together. And so you'll see here that the sum shows that attractive forces bring ions closer and closer together, and at some point this attractive force is getting negated or canceled by the repulsive force as nuclei start to repel one another due to the protons of positive charge repelling the neighboring nucleus away. And at some point we cross the x-axis and we have no net force, and we would establish the ideal bond length for these ions. And if we try to bring the two ions even closer, the dominant force is now the repulsive force, and we're going to cross the x-axis and go into the negative force territory.